thought we would do that by showing you a short little video about what we've covered so far, and it's going to be very short and very fast, so hold on and buckle your seatbelts and get ready. And as you go through this, try to remember all of the things that we've talked about, and if you can remember your impressions as we talked about them throughout the year. So here we go. First of all, we started talking about different kinds of numbers, such as integers, rational numbers, and the like. And we mentioned the rules for adding, subtracting, multiplying, and dividing integers. And we tried to emphasize that we would be using this idea of adding, subtracting, and multiplying or dividing integers in just about every algebraic application that we do throughout the year. And so far, hopefully you've seen this, and we'll keep emphasizing that. We then talked about what a basic algebraic expression was, which is just a small little mathematical sentence that may have a variable in it, and it just describes some type of a mathematical operation. These expressions come in all kinds of shapes and sizes. Then we talked about what a basic equation is, and that's basically just one algebraic expression set equal to another algebraic expression. And sometimes we have to solve these equations or evaluate these expressions for a particular application that we're working on. The rules that we mentioned in order to do that were the order of operations, please excuse my dear Aunt Sally, and inverse operations used to solve or simplify expressions and equations. We've kind of practiced using those rules in different ways throughout the first half of the year. Then we practiced solving equations. We started out with one-step equations and moved on to two-step, multi-step, and multi-step with even with parentheses on both sides of the equal sign. And most of you were able to do that quite successfully. Another thing that we even saw toward the end of that unit was that some of those equations have no or infinite solutions. And they were just a little bit unusual when you solved them. Another tool for simplifying expressions and solving equations is called collecting like terms. Like terms are terms that have the same variable to the same power in them. Our little example here, we have several terms with an x in them on the left side with equal to 24 on the right side. Well, we can combine all of those x terms together by just adding or subtracting the coefficients. So 3 plus 4 is 7, 7 minus 7 is 0, 0 plus 8 is 8, so we end up with 8x equals 24. And when we divide by 8, we end up with x equals 3. Inverse operations sometimes can take a little bit of time and are a little bit tedious. For example, if I try to add 4x to both sides on this one, and then subtract 5 from both sides to try and get all the x's on the left side, all the constants on the right side, that can take a little bit of time. So we tried to simplify that a little bit by showing you that sometimes we think of the equal sign as this great barrier we called it the Great Wall of China just for fun, but it's really not a mystery. In fact, we showed that terms, an entire term like 4x or 2x can be moved from one side of the Great Wall or the equal sign to the other by simply reversing its sign. If it's negative on one side, it becomes positive on the other side. And so here's an example of how I moved all the x's to the left side and all the constants to the right and what their signs would look like if I did that. By doing that, we made inverse operations a little easier. We kind of streamlined the process and made it so it was quicker and not so frightening or tedious. Next, we moved on to using what we call linear equations. Linear equations are equations that look like this. They have two variables in them. The variables cannot have exponents bigger than 1 in them. None of the variables can be in the denominator of a fraction. If those kinds of things take place, if you graph this equation, you end up with something that isn't a straight line. And linear equations means you have a straight line. The solutions to a linear equation consist of two numbers, an x and a y value, called an ordered pair. these solutions are infinite in nature and line up on a line that we learned to graph. So I can think of an infinite number of ways that you can add two numbers together that equal 10, and we can graph a lot of those on a coordinate system, but if we went out very far, it would take too much time and space to try and illustrate that. So we usually stay pretty close to the origin or the 0, 0 point on a coordinate system when we graph it. We found that graphing linear equations on a coordinate system is quite easy. It is especially easy when we solve an equation for y and write it in a y equals mx plus b form. When we solve the equation like that, the act of solving it for y and leaving a number in front of x, the number in front of x, which we called m, is actually the slope of the line that you would graph from that equation. Any number behind x that we called b is actually the y-intercept of the graph. So even if you did not graph, or if you did not solve the equation for y first, if you just, by guess and check, graphed a bunch of points using the original equation, you would eventually find out that it does cross the y-axis, what we call the y-intercept, and the line would have a slope of what m is if you did solve it for y. Okay, so we learned that if an equation was rearranged into y equals mx plus b form, you just need to start at the y-intercept and then use the slope. So on this one, you would start at 4. You'd go up to 4 on the y-axis, and then the slope says to go over 2 and up 1, or you can go up 1 and over 2, whatever makes the most sense to you. And then you got your second point, and then you can just sketch a line through all of those points, and you've got your graph. Here's an example of y equals 2x plus 4. Here's an example of y equals negative 2x plus 2. This y equals mx plus b form that we learned to write by solving a linear equation for y is called slope-intercept form. We also saw that if you know the slope of a line and its y-intercept, where it crosses the y-axis, that you can write the equation that way. So if you just have those two pieces of information, you can actually write the equation. For example, if m is 1/2 and b equals 4, the equation is y equals 1/2 x plus 4. We did mention that if you look at just a few points on a line on a coordinate system, you can actually trace that line and you can find the slope and see where it crosses the y-axis and write the equation that way as well. We found that some real-world problems can be solved using 2 or more linear equations called as systems of equations. We learned to solve these systems of equations by graphing them both and seeing where they intersect, or using a process we call substitution. And the last process that we learned was elimination, and that's where we ended up adding the two equations together if there was an opposite in them, or we would multiply by -1 to create an opposite, or we would multiply by some number to create an opposite in either the x or the y column, and then we could finish solving the system of equations. Last week, we talked about functions. We asked you to think of y equals mx plus b equations as a little computer program with inputs and outputs. We even showed you a crazy video about animals going into the meat processing plant, and an animal would go in, like a chicken would go in one side and out would come the chicken nuggets. That was a little bit graphic, but it was hopefully get the point across what happens here with these little function machines. So if you have a x value that goes into your function, and here's our function, y equals 2x plus 10, these x values we call the domain, or the input. They would go into the function, get multiplied by 2, then end up being these three numbers, and then we would add 10 to that result, and out would come the output. And the output are the y values, or the range, and so that's something that we wanted you to remember. Okay, in a function, each input can only have one output. So if If an input has more than one output, it's not considered to be a function. You've got some other type of relationship there. We also mentioned function notation. That's where you write an equation like y equals 5x minus 4 like this. F of x equals 5x minus 4. Now f of x and y are interchangeable, but this is just saying we have a function that's a function of x over here. And then we could easily say, well, what if we wanted to put 3 into this function and find out what it equals? And that made it easy to do by just putting a 3 right here and then putting the 3 right there. And then just on the right side doing 5 times 3 minus 4, which in this case equals 11. We finished up by saying, how can you tell if a function is linear? And that was our last lesson, linear versus nonlinear. And if it has a constant rate of change, we saw that either by looking at a set of ordered pairs or looking on a graph, or if it's graphed, it is a straight line, or if the equation can be written in the form of y equals mx plus b, where x can't have a power on it other than 1, and x can't be in the denominator of any side of the equation. So that kind of wraps up what we learned about, and we're going to give you a little review assignment, and then we'll move on to the laws of exponents. Thank you very much.